Hello, and welcome to Linear Algebra. This is Lecture 3, the geometry of linear systems. So, last time, we talked about Gaussian illumination. Right? So this is about how using row operations, we can put any matrix into reduced row echelon form. And we saw how if you start with a linear system of equations, you form their augmented matrix, you put it into reduced row echelon form, and this tells you whether or not the system has solutions, if it has a unique solution, if it has multiple solutions. And since you can always solve for the pivot variables in terms of the free variables, it gives you all of the solutions to the system when it has any. Okay, this time, we want to talk about a geometric interpretation of a linear system. Okay, so let's start with vectors. An n-dimensional vector over R is a column V with entries V1, V2 up to Vn, with Vi a real number for every I. The set of n-dimensional vectors over R is denoted Rn. Right? R raised to the nth power, which we'll just pronounce Rn. Okay. We have two algebraic operations. On Rn. One of them is scalar multiplication. So here, if you give me a real number and you give me an element of Rn, then we can multiply them together and create another element of Rn. So this would be the vector, so C times V. Well, if V had coordinates V1 through Vn, then C times V has coordinates CV1 through CVn. Okay, and then the second operation is vector addition. So here, if you give me two vectors inside Rn, then we can put them together to form another vector, V plus W, inside Rn. So this is the vector V plus W. Well, if V had coordinates V1 through Vn, and W had coordinates W1 through Wn, then V plus W has coordinates V1 plus W1 through Vn plus Wn. Okay, so later we will see that any set with these two operations is called the vector space. So what we're saying at the moment is that Rn is a vector space. Now, in a vector space, here is an interesting thing you can do. If I give you a bunch of vectors and I allow you to use these two operations, I want to know what other vectors can you construct, right? So we're going to say that a linear combination of a set of vectors, say v1 through vk, inside Rn, is a vector of the form c1 v1 plus ... up to ck vk. Right? Here we'll introduce notation, which you may already be familiar with, sigma notation for sums. So this says sum these terms where your parameter I starts at 1 and goes up by 1 until you reach k. Right? So this is just a more compact way of writing this. And here, all we want is the ci to be real numbers for every I. Okay, so linear combination is any vector of this form. Right? So I give you v1 through vk, and now you're allowed to do scalar multiplication and vector addition, and these are the vectors you can construct in that way. The set of all such vectors is going to be called the span. So the span of v1 through vk is the set, and we'll either denote it by writing out span of v1 through vk, or we'll use angular brackets and then just put the list v1 through vk. This is the set of all linear combinations of these vectors. Right, so formally we could say that this symbol, the square brackets v1 through vk, this represents the set of all of the sums, I goes from 1 to k, of ci, vi, where the ci's are arbitrary real numbers. Okay, so linear combinations and spans are something we're going to be working with all the time from now on. Let's do an example. Let's phrase it as a question. So, for example, is the vector w with coordinates 39, 34, 26, a linear combination of the vectors v1, coordinates 3, 2, 1, v2 with coordinates 2, 3, 2, v3 with coordinates 1, 1, 3. Okay. So we can ask ourselves this question: is this given vector a linear combination of these three? Is this vector inside the span of these three vectors? Okay, so an equivalent way of asking this is, can we find C1, C2, C3 in the real numbers such that C1, V1 plus C2, V2 plus C3, V3 is equal to W, right? That's the exact same question, right? Because every linear combination of v1, v2, v3 is a vector that looks like this. And so we're just asking, can you find a vector that looks like this, which is equal to w? Okay, so putting in the vectors, putting in the coordinates, this is the same as asking, can we find C1, C2, C3 such that C1 times 3, 2, 1 plus C2 times 2, 3, 2 plus C3 times 1, 1, 3 is equal to W. W was 39, 34, 26. Okay. Okay, well, this is still equivalent to asking. So let's just do the vector addition directly here. So can we find C1, C2, C3 real numbers such that 3C1 plus 2C2 plus C3, and then 2C1 plus 3C2 plus C3, and then C1 plus 2C2 plus 3C3 is equal to 39, 34, 26. Right? Well, that's the same as asking, can we solve three C1 plus 2C2 plus C3 equals 39, 2C1 plus 3C2 plus C3 is equal to 34, and C1 plus 2C2 plus 3C3 is equal to 26. Well, and the answer is yes, because this is the Chinese example from the previous lectures. This is the example we saw from the 8th chapter of the 9 chapters on the mathematical art from ancient China. And we found that it has a unique solution. So solving this system of equations is equivalent to figuring out, is this vector a linear combination of these vectors? Okay, great. Here's another example about linear combinations. Any vector, say vector x with coordinates x1, x2, dot, dot, dot to xn, can be written. Okay, well, one thing you could do is pull out the coordinate x1 and keep the vector 1, 0, dot, 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 0. And then add to that x2 times the vector 0, 1, 0, and then zeros, dot, 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 until you add xn times the vector 0, dot, 0, 1. Right? So I can always just use these vectors that have zeros everywhere except for one spot, and that spot is a 1, and just multiply them by the coordinates, add them together, and I get the vector I started with. So we'll give these names. This vector will be denoted E1. This vector will be denoted E2. This vector will be denoted En. Right? So in general, EJ would be the vector that has zeros everywhere except a 1 in the jth spot. Right? And these vectors will come up so much that we give the set a name. So we call this list, E1 through En, the standard basis of R. Later, we'll talk about what basis means. But at the moment, just know that this is called the standard basis of Ra. This notation, when I use round brackets instead of squiggly brackets to denote a set, I mean that I care about the order. So I'll talk about this being a list as opposed to a set. A list is just going to be a set where the elements are in a fixed order. Okay, so this list of vectors is known as the standard basis of Rn. Okay, let's do another example. Let's say that our vectors are v1, 1, 0, 0, v2, 1, 1, 0, and v3, 2, 1, 0. And now let's notice that any vector, let's say a vector, w, with coordinates w1, w2, w3, is inside the span of v1, v2, v3, if and only if w3 is equal to 0. Third coordinate of the vector w is equal to 0. Okay, so it's an if and only if, so to prove it, we have to prove both directions. So one direction is clear, right? If the vector is in the span of these three vectors, then the third coordinate has to be 0, right? And that's clear because if you're in the span of these three vectors, that means that you're obtained from v1, v2, v3 by picking three constants, multiplying these vectors by those constants, and then adding them together, right? And no matter what constants you pick, a multiple of v1 is always going to have the third coordinate equal to 0. A multiple of v2 is going to have the third coordinate equal to 0. A multiple of v3 is going to have the third coordinate equal to 0. And if you add vectors whose third coordinate is equal to 0, the third coordinate is still equal to 0. So one direction is clear. To see that the other direction is true, right? So to see the other direction, what we have to notice, we have to show, is that if the third coordinate is equal to 0, then the vector is in the span, right? Said differently, the third coordinate is equal to 0 means that I can find constants c1, c2, c3, so that c1 times v1 plus c2 times v2 plus c3 times v3 gives me w. Okay. But to see that this is true, note that we can write w, so this arbitrary w, w1, w2, w3, with w3 equal to 0. We can write it as, say, w2 times 1, 1, 0 plus w1 minus w2 times 1, 0, 0. Okay? So that is to say, this is w2 v2 plus w2 minus w1 v1. Okay? So this is easy because this w2 times this vector, well, that has the same second coordinate as w. It doesn't have the, and it has the same third coordinate because 0. The first coordinate might not be the same, but we can always fix that by using v1 because v1 only has non-zero first coordinate, right? Of course, we could have decided to get the second coordinate using v3, and that would also have worked. So alternately, we can write w as w2 times 2, 1, 0 plus w1 minus 2 w2 times 1, 0, 0. And so that's w2 times v3 plus w1 minus, oh, sorry, minus 2 w2 v1. So in this case, w is a linear combination of v1, v2, v3 in more than one way. Right, so yeah, sometimes you'll have a unique solution to a system of equations, and sometimes you'll have multiple solutions to a system of linear equations. Also, sometimes you won't have any solutions, in which case we would have found that the vector was not a linear combination, right? For example, in this case, if we started with a w whose third coordinate was not 0, the system of linear equations we would write would be inconsistent. There would be no solution. Okay, so we have an equivalence of problems. Solve a system of linear equations, a linear system. Of equations is equivalent to write a vector as a linear combination of given vectors. Okay, so geometrically, okay, so let's start with things that you already know. If I have a vector with coordinates 1, 2, then I can represent this geometrically by putting the x-axis, the y-axis, and then I count out 1 on the x-axis and 2 on the y-axis, and I see where these would meet, and I join the beginning, the origin with that endpoint, and this represents the vector v. Right? Also, the length of v is the square root of 1 squared plus 2 squared, right? By the Pythagorean theorem directly from the picture. Similarly, if we go up a dimension, let's say that w has coordinates 1, 2, 3, then the way you would represent this is you would draw the 3 axes. So let's say we put the x1 here, the y-axis here, and the z-axis there. And then you would trace out these equal distances. And what you would do is you'd want to go 1 in the x-axis, 2 in the y-axis, 3 in the z-axis. And let's see how well I can draw this. So here I'm drawing parallel to the x-axis, starting there. And then this is meant to be parallel to the y-axis, starting there. And so there I find this point with coordinates 1, 2, 0. What I want is to translate that up by 3 units. So here I could similarly draw the parallel to the x-axis, parallel to the y-axis. Up at 1, I draw another parallel. At 2, I draw another parallel. I end up with this point. So now that has the correct coordinates. So I join the origin with that final point. And this represents the vector w. I also have the length of this vector, which again, from the picture and the Pythagorean theorem, you can easily compute that its length would be the square root of the sum of the squares of its coordinates. Okay, so that's how we represent vectors geometrically. Now we have these two operations. Which have geometric interpretations. So if you multiply v by a scalar c, then, okay, well, first let's notice that the length of this, as you can work out quickly using the formula, this just multiplies the length of V by the absolute value of C. And it points in the same direction as V if C is positive, points in the opposite direction as V if C is negative, right? So we can determine a vector just by knowing its length and what direction it's pointing. And so here we go. The length gets multiplied by the absolute value of C, and the direction either stays the same or becomes exactly the opposite, depending on the sign of C. Of course, if you multiply by 0, you just get the 0 vector, to which we don't assign a direction, or we assign all directions, depending on what convention we were using. Similarly, if you do vector addition, this also has a geometric interpretation. So this is the vector obtained by moving one of the vectors from the origin to the tip of the other vector. So for example, let's say that here I have x-axis and y-axis, and then my vector v looks like that, and my vector w looks like that. Then what I would do is I would move the vector w to start at the end of v, or I would move the vector v to start at the end of w, right? So this would be v starting at tip of w, while this would be w starting at tip of v. And the resulting vector is the sum. So that would be from the origin to this endpoint. This is v plus w. Okay. The span of a non-zero vector v, right? So by definition, this would just be c times v, where c is an arbitrary real number, right? Well, we just saw geometrically all you're doing is changing the length of v, right? Either pointing in the same direction or pointing in exact opposite direction. So this is the line through the origin in the direction of v, right? So if my vector v looks like this, then this would be 2 times v, this would be minus v, this would be minus 2 times v, and altogether I end up with the span of v. It's that line. Right? If w is a fixed vector, then the set w plus c times v, where c is a real number, right, which with abusive notation we could write as w plus the span of v. This is the line parallel to the line we just drew, the span of v, passing through end of W. So let's say that this is W and this is V, like we had before. Then W plus V would look like that. It would be this point, say, would end at this point. W plus 0 times V would end at this point. W plus 1/2 times V would end at this point. And W plus minus V would end at this point. And altogether, we just end up with this line, W plus the span of V. Okay. Let's look at another example. So last lecture, we saw that the system of equations x plus 1/4 y plus 1/2 w equal to 20, 2x plus 1/4 y equals 36, x plus 8c plus w equals 176. Has solutions. X is equal to 16 plus 1/2 w, y is equal to 16 minus 4w, z is equal to 20 minus 3 over 16w. So remember, in this case, we found that w was a free variable, and x, y, and z were pivot variables. So solving the system meant writing the pivot variables in terms of the free variables. So here, these are the solutions where w is an arbitrary real number. If we write these as vectors, the solutions are, well, our vectors would have 4 entries, x, y, z, and w. Okay, now what do we know about x? X is equal to 16 plus 1/2 w. Y, 16 minus 4w. Z is 20 minus 3/16 w. And finally, w is just w. So now I can pull out the constants into a single vector. So 16, 16, 20, 0. And then the multiples of w, I'll pull out at w and end up with 1/2 minus 4 minus 3 over 16 is 1. Okay, now we recognize this is exactly the sort of thing we were just drawing, right? Geometrically, this is a line in R4. Right? It is the line through the point 16, 16, 20, 0 in the direction (1/2 minus 4 minus 3 over 16, 1). Right? So even though I can't draw it in R4, the picture in R2 tells you what this is going to look like. It's just you take this line and you translate it to the end of this vector. Right? Let's do another example. So the system x1 plus 2x2 plus 5x4 equal to minus 3 minus x1 minus 2x2 plus x3 minus 6x4 plus x5 is equal to 2, and minus 2x1 minus 4x2 minus 10x4 plus x5 is equal to 8. This has solutions. X1 is equal to minus 3 minus 2x2 minus 5x4. X3 is equal to 1 plus x4, and x5 is equal to -2, with x2 and x4 arbitrary real numbers. So in this case, x1, x3, x5 are pivot variables, and x2, x4 are free variables. Right? They're allowed to be any real numbers. Right, let's write that down. So here we're using x2 and x4 as free variables, and x1, x3, x5 as pivot variables. Okay, so writing the solutions as vectors, they are, okay, so our vectors have 5 entries, so x1, x2, x3, x4, x5. Okay, now x1 I can write as -3 minus 2x2 minus 5x4. x2 is a free variable, so it's just x2. x3 is 1 plus x4. x4 is a free variable, so it's just x4. And x5 is -2. Okay, so I'll do the same thing we did a moment ago. I'm going to first write a vector with all of the constants. So each variable will contribute a constant. Then I'm going to have multiples of each of the free variables. So x2 occurs here with a -2, here with a 1, and zeros everywhere else. And then x4 occurs here as a -5, 0, 1, 1, 0. Okay. So we see that this is, so end here, x2, x4 are arbitrary real numbers. So we recognize this as the, this is equal to this vector, -3, 0, 1, 0, -2, plus the span of these two vectors. Right? Or geometrically, this is the translate of the plane, this span of these two vectors is going to give us a plane in R5 through the point -3, 0, 1, 0, -2. Right, so we can't draw things in R5, but we can visualize this by using R3. So we can visualize this. So if you give me 3 vectors, if v1, v2, v3 in R3 are non-zero vectors, not all on the same plane, then okay, well, what's the, well, let's say v1, v2, w. Okay, so here is R3, and let's say you have v1 and v2 like that, so then the plane containing them looks like this. W is not on that plane, so let's say W something like that, then W plus the span is going to look like this. This is W plus the span of V1, V2. Okay, so that's the picture. It's much easier. It's possible to draw it in R3, and then this is the visualization of what's happening in R5. Okay, so we'll stop there for today and pick it up there next lecture.